In this video, we'll discuss why the trajectory of a planet around the Sun or that of a star in a binary star system has to be an ellipse. Let's try to prove that. Suppose we have two stars with us, M1 and M2, and we are assuming there is no third body around them. So it is an isolated system. Now, to prove the trajectory, first we need to write down what forces are acting on any one of them, and then we proceed from there on. So basically we start with our dynamics equation F equal to ma. Let's start with analyzing star number 2. So for M2 we'll write the net force equal to mass times acceleration. Now the net force on M2 is the gravitational force due to M1. That is the only force that is available on star number 2. So therefore our LHS will become some function, let's call it f, dependent on the separation between them, let's call it r, multiplied by r cap. Now since we are using lowercase r, we need to define what it is. So the r vector is from m1 to m2. This is our r vector. That means it is the position vector of star number 2 if we sit on star number 1. Now the RHS is m2 multiplied by the double differentiation of the position vector of star number 2. Now the trajectory is being seen by an inertial observer. Suppose we are that inertial observer standing somewhere here, and we are looking at star number 2. So the position vector of star number 2 with respect to us is something like this. So this is the vector whose double differentiation we need to take. This is our R2. Now R2 can be written as the vector sum of two different vectors, that is the position vector of the center of mass plus the position vector of star number 2 with respect to the center of mass. So suppose here is our center of mass of this binary star system. So therefore from the triangle rule I can say that this R2 vector will be position vector of the center of mass, that is this vector, plus a fraction of r vector. Now that fraction we already know, that can be written as m1 by m1 plus m2 multiplied by the r vector. Let's put this value in our starting equation of second law. So this becomes m2 multiplied by rcm double dot plus m1 by m1 plus m2, whatever we have. Now we can easily see that the first vector is a null vector because the system is isolated. So since there is no third body, so the center of mass of these two bodies combined will have a zero acceleration. Hence our equation becomes FR r cap equal to, now a mass which is neither m1 nor m2 but which is less than both of them, that is m1 m2 by m1 plus m2 multiplied by r vector double dot. So if we try to see this equation physically, it is like Newton's second law applied to a new body whose mass is this much. Usually we call this as a reduced mass because this is less than both m1 as well as m2. Let us denote this by the symbol mu. So our equation becomes LHS remaining the same, FR r cap equal to mu r vector double dot. So we have converted the whole binary star problem into a single star problem. Now, if we analyze this equation further, we have a new star having a mass mu, and the source of the force is applying the same force as was in the original binary star system, because we can see that the LHS does not change. It is still FR r cap. Now, what happens if the force is of the form FR r cap? We can make one conclusion, that since the force is always passing through the source, let us call that as our origin. Therefore, the torque of that force about the origin will be a null vector. So, torque about the origin O will be a null vector. If that is the case, we can conclude that the angular momentum of this reduced mass about O will be a constant vector. Now, what help will this result give us? A constant angular momentum ensures that the motion is confined to two dimensions only. Let us try to prove that. Suppose we have our three axes x, y and z. This is our x, suppose, y and z. And let us suppose for the time being that our angular momentum, which is a constant vector, is suppose pointing in the z direction. This is our LO. Now, since the angular momentum by definition is the cross product of two vectors, which are the position vector and the linear momentum, hence we can conclude that both of these must be in the xy plane. That is the only option left. Why? Because the angular momentum is in the z direction, and if both of these are in the xy plane, we can easily conclude that the motion is happening only in the xy plane. So we need not worry about 3 dimensions. We can just solve this whole situation by taking only 2 coordinates. Now here we again have a choice. Either we can deal with x comma y, or we can deal with r comma theta. Now, since r is involved in the function fr from the law of gravitation, so we will try to use r comma theta instead of x comma y. So r comma theta is the method of representing the position of any particle in terms of how far it is from the origin and what angle it is making from the reference axis, which is usually taken as the x-axis. So here is our reduced mass, and here is our sun, or whatever is the source of that force. Now let's try to find out what is this constant vector equal to. Now r vector, we can easily see, can be simply written as r cap, and for p vector we will need the differentiation of the r vector. So let us differentiate this vector. Now we must remember that here there are two position vectors which are important. Instead of x cap and y cap, the two position vectors are the r cap and the another one is the theta cap, the direction in which theta will increase. So this is our r cap, this is 90 degrees, and this is our theta cap. So once we are clear with the unit vectors that we will be needing here, we can proceed for r vector dot. So I'll have to differentiate this one by one by the product rule. So we get r dot r cap plus r theta dot theta cap, and this is very physical also. R dot changes our separation from the origin, and r theta dot is our r omega, which we already know from the circular motion. Now since we know these two vectors, I can write down the angular momentum. So L vector about the origin r cap cross r dot r cap plus r theta dot theta cap. Now this is r square theta dot, and the direction will be z cap. Now I have missed the mass here because I have just written r cross r dot, so I must write mu here also. So this is our constant vector. Let us continue. So we have found out that the angular momentum about the origin is mu r square theta dot z cap, and we also know that this vector is a constant in this given situation. Now z cap is anyways a constant. It has a constant length of 1 and it has a constant direction pointing along the z axis. So what that means is that whatever is remaining must also be a constant, because this whole thing is a constant. So let us give it some symbol. Let's call this as lowercase l. That means this lowercase l is a constant. That would mean that r and theta dot are changing such that mu r square theta dot must remain a constant. So therefore from here we get one relation, which is that d theta by dt is equal to L upon mu r square. Let's call this equation number 1. Now since we are attempting to find out the shape of the trajectory, that means we must somehow manage to get dr by dt also. Now this first equation came from the knowledge that the force FR cap is a central force. That led us to conclude that the angular momentum is a constant. What further we can say is that this force, since it is conservative, then the total energy must also be constant. So therefore the sum of the kinetic energy as well as the potential energy must be some constant. Let's call that as E naught. Now kinetic energy will be half mu multiplied by speed square plus, now the potential energy will be minus g m1 m2 divided by r. Now this speed we can easily find out by taking the modulus of the r dot vector, which we have already done. So I will write down it directly now. So this will be r dot square plus r theta dot square plus, now g m1 m2 is anyways a constant, so let's call this as some capital C, minus c by r equal to E naught. Now theta dot can be eliminated from equation number 1. Theta dot is L by mu r square. This implies, let's solve this further, half mu r dot square plus, now we get L square by mu square r square plus the potential energy, let's call that as UR, is equal to E naught. This implies half mu r dot square, let's keep this one side. Now what we have remaining is the potential energy plus another term which depends on the angular momentum, because we have a small l here, L square by 2 mu r square equal to E naught. Now let us have a look at this equation. All of the parameters on the LHS are dependent on r only. Somehow we have got rid of the parameter theta. As we can see, we don't need that anymore. This is another simplification that we have been able to achieve. So all of this equation is a one-dimensional equation and the variable is r. So we have achieved two simplifications. First, we reduced everything to a single star of having mass mu, which is a reduced mass. Further, we converted the problem to a one-dimensional problem. Now this equation will give us the dr by dt. So for analyzing dr by dt a little more, let us talk about this function, which is generally referred to as the U effective. The name does not matter much. What we must understand is how this function is behaving. So effectively, we have got something like this: half mu r dot square plus some function which we are calling the effective potential energy for one dimension as a function of r equal to some constant E naught. Now let us talk about this, how this function varies with time. So if we, not time, as a function of r, so if we draw our axis, this is the y-axis for the U effective, and let us suppose this is the r-axis. Now this function has a shape like this. Now how will this help us? Let's see that. So to analyze how this leads us to the equation of an ellipse, let us first write it down mathematically as what is dr by dt. So from here, dr by dt, that means the rate of change of the separation of that planet from our sun, comes out to be plus or minus under root 2 by mu, whatever is that, E naught minus U effective r. And this is the graph of U effective. Therefore, E naught will decide what kind of a rate R has with respect to time. Now, if E naught, which is a constant, is somewhere here, if it's a positive quantity, let's call that as case number 1. So, for case number 1, we are saying that let us suppose that E naught is positive. Now, when we will solve this equation number 2 with equation number 1, by dividing these two, we get a differential equation in r and theta. When that is solved for case number 1, we get r theta as a hyperbola. Case number 2, case number 2 is when E naught is exactly 0. Now again, if we do the differential equation solution, we get it to be a parabola. Remember the significance of the point of intersection. Now this is the point where we will get dr by dt to be 0. Hence this point gives us the r minima for case number 1, and for case number 2 this is our r minima. So this is as close as possible that a planet would arrive to our sun. And for both of these cases, we can easily notice that R max is infinite. That is why these possibilities are sometimes referred to as open orbits. The planet never returns anywhere near the sun. Now let's see case number 3. Case number 3 is if we are somewhere here. That means we are at a negative E naught. Now again, if we solve equation number 1 and 2, we get r theta as r naught by 1 minus e cos theta, where e is the eccentricity. This is the equation of an ellipse. And finally, if we have a very special case, if we are exactly at the minima of this, that means only one point is relevant, and at that point dr by dt is 0. That means r always remains a constant. So for case number 4, E naught is some particular value, some unique particular value. So for that unique value, we get it to be a circle. I hope this video helped you in some way. Thank you for watching.